Hello and welcome to EP2CM4 topic number 4, electricity and magnetism. This week we're going to look at a little bit of a slice of this huge exciting field. Specifically, we're going to focus on how electric field and voltage behave in regions with either empty space or fixed charge density or linear dielectrics, where Gauss's law says that the divergence of the electric displacement field is the free charge density, and in the electric displacement field itself is proportional to the electric field via the permittivity. And we're also going to look at how current flows and dissipates energy in an imperfect conductor, where Ohm's law relates the current density to the electric field via conductivity, and charge conservation tells us how the divergence of current density is going to be related to the rate of change of the charge density. First up, voltage, electric field, and Gauss's law. The force on a point charge Q is Q times the electric field. So Q is a scalar, but the electric field being a vector gives us a force vector. E is the electric field caused by everything except that charge. So the charge itself does create an electric field, but this electric field is seen by things besides that charge. Okay, electric field satisfies Gauss's law, which says that the divergence of the electric field, this is in differential form. There's also an integral form that you might be more familiar with that you can convert to this by the divergence theorem. Divergence of the electric field is the charge density rho over epsilon naught. Rho is the charge density that is per unit volume, that kind of density, and epsilon naught, the permittivity of free space, is 8.854, etc., times 10 to the negative 12 seconds to the fourth amps squared per cubic meter kilogram, or second squared coulomb squared per kilogram meter cubed. Right. Okay, so Coulomb force is conservative, so that means it's the gradient of a potential function. We'll look at some perhaps complications to this later when we get to magnetic vector potential in a challenge topic. Well, really, it's in the notes. It's more of an optional thing. But at least for magnetostatics, it's fair to say that the electric field is the negative gradient of the electric potential. The electric potential, also known as voltage. So if we start off with looking at the work that is done by the Coulomb force as you move a charge from one point to another and have a change in potential energy associated with it, the work done by the Coulomb force would be negative its change in potential energy. So if it's losing potential energy, then it means it's doing work. If it's gaining potential energy, work is being done on it. Okay, so work is force dotted with a little bit of displacement, and this is now we're putting it in terms of a differential change in potential energy. And if the force is QE, then we can substitute that in. And now per charge, we've got that E dot dr is negative 1 over Q du, and if we define that electric potential is the potential energy per unit charge, then this tells us over a, if one step in some direction is E dot dr is negative dV, then E itself, this works out if E is the negative gradient of the electric potential. And you can kind of see how this works with gradient if you think about it in one dimension. So in one dimension, then we've just got E dx equals negative dV, and then divide by the dx, we got E is negative dV by dx. And so that's the one-dimensional version of it. All that the dr does is it helps convert this into 3 dimensions. So for any little change in voltage in some direction, if the voltage is increasing in that direction, then the electric field points in, the electric field has to point in the opposite of that direction. So electric field points in the direction of fastest decrease of electric potential. So it's negative the gradient of V. All right, now we're going to look at an example, electric field from a uniformly charged rod. So this is something that you might remember from dealing with it before. If you have a circular cross section and it's very long, and we have then you have charge inside, that's let's say 3 coulombs per cubic meter, this volumetric charge density, then we want to figure out what the electric field is inside and outside the rod. And you might remember something from your electromagnetism course that tells you the electric field is going to be something like this. So it increases linearly inside the rod, and then outside the rod, it decreases like 1 over r. This is kind of like a line charge. It has some something that's equivalent to the charge per unit length, sort of, and then goes, drops off like 1 over r. This might be a relationship that you kind of remember. Anyway, this is we're not going to analytically derive it. Rather, what we're going to do is use our simulation software and see if we can check whether this result actually holds. So we've loaded up FlexPDE here, and we've got a new file, and we can set it up to work with this. So let's call it. We can make some title for this thing. Let's call it uniformly charged rod, and we'll still stick in 2D because there's nothing changing in Z along the length of this rod. So we shouldn't expect that anything should depend on that. So we can just do a 2D simulation and get hopefully better accuracy there. Now, the way to set this up is to actually use the electric potential as the variable. Then under the definition section, we can say what epsilon naught is. So if you forget what that is, then you can go back up to the top where we wrote that out there. So epsilon naught is equal to 8.854 E minus 12. Then the electric field is negative the gradient of the electric potential. And we've got the differential equation that is Gauss's law. So div of E should be equal to rho over epsilon naught. Div E is rho over epsilon, I guess I called it ep0 here. Okay, so then that's going to be solving Gauss's law. So E negative grad V. This is all really an equation just in terms of electric potential. And by writing it out like this, we don't have to write as many things down there, and we can also figure out what the electric field is later. All right, so they tell us that we want to figure that out in this case for a uniformly charged rod that has a radius of 0.5 meters. So we'll start off by, let's say, region rod, and we'll start at our rod. Let's give this a variable name too. This will be the radius of the rod, 0.5. Start our rod 0, and then we're just going to draw a circle by saying arc, center equals 0, 0, angle is 360. Okay, so there's the drawing of the rod there, and we can say contour of V just to check that the shape works out. Oh yeah, I need to define rho. So let's say rho is equal to 0 for now. Okay, this isn't doing anything. We're just checking that the arc drew correctly, and we're all good there. All right. So inside the rod, we have one charge density, and outside the rod, we're going to have a different charge density. So rho equals 0 might be a good default charge density, but we're going to redefine this inside the rod region. And this will be rho is equal to 3 coulombs per cubic meter. Okay, so we still have pretty much nothing happening. It looks like the electric potential is this massive number, and that's because we don't really have a reference for this. So we can say that the electric potential on the boundary of this circle is equal to 0. Value V is 0, and now we've got some reference. So if V is fixed to 0 on the outside, then we've got an increasing potential as we move out. Let's make some plots here. So we'll make this painted. Now we can see the electric potential going to 0 here. And the electric potential, sorry, did I say increasing? It's decreasing as we move out. It's increasing more towards the center because we've got more electric field pointing out from there. So we would have the most energy if a test charge is placed in the center of this rod. If it's positive, then a little bit of motion off to the side will let it fly out towards the end there where we're holding it at a potential of 0. So pretty high electric potential inside this thing. And what else do we have? We can make a plot of the electric field with vector. Great. So the electric field starts off very low in the center and then increasing as we move out. Next thing we can do is we can compare this with the theoretical value. So let's put in what the theoretical E is. E theory is rho times R over 2 times epsilon naught. And conveniently, R is already built into FlexPDE as the root of x squared plus y squared. So we can make a plot of how this of how this magnitude compares to the magnitude of the electric field here by using an elevation plot. Elevation, and we'll just type in the thing that we want to plot. So let's plot first E theory from 0, 0 to R rod 0. Okay. So rises completely linearly here, up to a maximum value of maybe 8.5 E10. And if we look at the plot of the electric field, it looks like it gets about the same size right at the end. We can add it to the elevation plot by just putting a comma here. Now this is a little bit tricky because E is a vector. It has two components. So this might separately plot the X and the Y components of E. Yeah. So you see along the line going horizontally, this is actually fine, I guess, because we expect E to be totally in the X direction and not at all in the Y direction. So this is maybe a little bit better than plotting the magnitude. It shows us both the magnitude and direction is what we would have expected from theory. But to make it a little bit easier to read and compare, maybe we want to just plot the magnitude of E. Like that. Or perhaps only the X component of E by dotting E with vector 1, 0, unit vector in the X direction. Okay, so pretty good comparison. Now, you might have noticed that we're only simulating this inside the rod, when in reality, we probably want to compare with what's going on outside the rod as well. To do that, we have to have a different region. And you actually have to put this region before the rod so that we're not overlapping and destroying this. Now, this can be whatever shape you like in general. It just has to be something that contains this so we can simulate this stuff inside of it. They tell us to do it inside a circle that's 5 times larger radius. So we'll do region, let's call it space. And here rho is going to be equal to 0. We don't need to redefine that because we put that as our default value. And we'll say start R rod, maybe R space. Let's do that. Our space is 5 times R rod. Start R space and 0. And then we'll go arc. Center is equal to 0, 0. Angle is 360. Okay, cool. So now let's see. We have an E field that goes up and then hits this value, hits this large value, and then stops. And then it's nothing. Okay, what's going on here? Well, we said that the electric potential on this surface is fixed to a fixed value of 0. It doesn't really matter what we set it to. We set it because it's sort of arbitrary what the reference point is. But having a fixed potential on that outer surface ends up being like having it as an equipotential. We've got a conductor on that outer surface. So it's isolating a little bit what's going on with the charge. It doesn't really know how to deal with stuff outside of this. It just says the electric potential outside of this is entirely 0. We can get perhaps a better result by, rather than defining 0 as the potential on that interior part, put the equipotential at the outside of space here. Okay, now what we have is that the voltage just increases as we go closer and closer to the center. It doesn't increase with the same slope though. We have the most electric field right at this edge, and then it sort of drops off outside of this. Now we can compare this to what's going on in theory by carrying this plot a little bit further. So first, let's take this plot not to R rod, but to R space. And that's going to give us a bit of a problem with the theoretical electric field, because we didn't define how that should behave differently outside of that region. So let's see. We said you said that E theory is equal to rho times R over 2 epsilon naught, right? And the rho is 0 outside of that center region. So probably what we need to do is say rho rod, make that its own variable, and say that this is if R is less than R rod, then rho rod times that, else R rod squared, just typing in this equation here, R rod squared times rho of the rod over 2 times R times epsilon naught. So this is something that's going to account for the electric field from theory both inside and outside the rod, and this should agree better with what we've got in the electric field. Yeah, okay, great, perfect. So it's linear inside and then drops off like 1 over R squared. So we successfully simulated what the electric field and the electric potential should look like for this setup. The next thing we're going to talk about is dielectrics and polarization. This is going to add us some complications to this. So a linear dielectric is a material where the polarization field that shows up in response to an externally applied electric field is linear in that electric field. So this means that you're going to have some, this is an artist's rendition of non-polarized atomic cores, and then you apply some electric field and everything lines up in a certain direction. So the external electric field, let's say applied to the right, is going to make the little positives on all the different atoms shift a little bit to the right, and all the little negatives shift a little bit to the left. And the net effect of all of this is an electric field itself that ends up pointing a little bit in the opposite direction. So how we work this out is we say that there's a polarization field that shows up, which is proportional to the electric field. And now this ends up leading to the externally applied electric field being partially canceled out inside, right? So because these things have moved, you can imagine inside the negative and positive maybe cancels out from like this one and the adjacent one. So with all those interior ones basically canceling out, the net effect is like you've got a little bit more positive on this whole end surface and a little bit more negative on this whole end surface, which creates an electric field that goes in the opposite direction and helps repel what's going on internally. You might be able to think that in electrostatics, a conductor is kind of like a dielectric that can infinitely polarize and completely cancel out any applied external electric field by just moving charge around as much as it needs to. The net effect of all of this stuff is that we can still say that the electric displacement is proportional to the electric field, just that the electric displacement vector is this this permittivity times electric field, where now that's not just the permittivity of free space, but perhaps increased by the susceptibility of the material, electric susceptibility of the material. Okay, so let's give a shot to adjusting this previous example by assuming that there's a material a little bit to the right, which is a dielectric. So what we expect is the dielectric will partially cancel the field from the from this charged rod here. Okay, so let's modify this. I'm going to maybe build something that's a little different than the example in the question. First, let's adjust things so that we're dealing with dielectrics. So what we'll say is that D is equal to epsilon times E, and we'll have to say what epsilon is. Epsilon is equal to ep naught times 1 plus chi E, where chi E is the susceptibility. And we'll also need to define that. So we'll say chi E by default is equal to 0 because not everything's a dielectric, but now we'll make one material where the material is a dielectric. So then what we'll do is we'll modify this equation to say divergence of D is equal to rho. And then if everything has worked out, then the previous example should still work. So let's test. Yeah, so we're still getting the electric field, agreeing with the previous theoretical electric field. Everything seems good here, no changes. Another thing we can do is try and plot the electric potential on this or maybe a different graph. It's got different units, but just to see how big it is relatively, we might try to plot that as well. Let's see. Okay, yeah. So we set up the electric potential so that it's relative to a 0 at this 2.5 meters away, and relative to that, looks like it rises up and then smoothly comes to this maximum around the center point there. Okay, so next we can modify things to add in a dielectric. Let's suppose that we've got a dielectric. We can put a dielectric in all kinds of different spots. Let's maybe put one right around here, and it doesn't have to be a circle. We can just draw a a rectangular shape to really see how this is going to bend and reject electric field. So let's have a new region. Dielectric. And we'll say in this region that we're going to start, well, actually, first we'll say chi E is equal to 10. So it's got a susceptibility of 10, which means it should be 10 times, well, really 11 times as good as free space at rejecting electric fields. All right, so then we'll start at, let's see, rather than the radius of the rod, let's start at r rod times 2 and negative r rod, line 2, r rod times 3, negative r rod, to r rod times 3 and positive r rod to r rod times 2 and positive r rod. Just drawing a rectangle here that's 2 times the rod radius high and 1 times the rod radius long to close. Okay, so here we go. We've got our dielectric right here, and look at that. It's bending the electric potential lines so that inside is more like an equipotential than it otherwise would be. It's not completely an equipotential because it doesn't have perfect susceptibility, but it does change what's going on with the electric potential as we go through it. As you go through this thing, then it's almost the same potential on one side as the other, right? And we end up with an electric field that is very reduced inside this thing, because what we're seeing here for the electric field is the sum of the electric field from free charges and the electric field from the what's called the bound charges inside the atomic cores moving around to create this polarization field. Okay, so we can compare this with what the D field would look like. Magnitude of D from, let's see, over the same range. So the D field a lot more continuous than the actual electric field in this region, but still having a little bit of this this different behavior than we had before we had the dielectric there. Okay, so here's E. Let's actually plot the vector of D as well. So this shows us some stuff. The electric field is largely reduced inside this, but not completely reduced to 0, just toward 0. Whereas the electric displacement field has been, is not really reduced, right? The electric displacement field almost uses this as a place to kind of increase and extend out to the, like, reach further from the interior here over to the right-hand side. So here's a fun thing. To the extent that the dielectric is like a conductor, where it's kind of rejecting the electric fields inside, we should be able to get something similar to this if we actually just made it a conductor and said, well, you know, let's just cut out the middleman and say that the electric potential on this thing is a fixed value. But it's a little bit difficult what value to choose, right? Because if you start off by saying, hey, you know, value of V is, I don't know, equal to 0 there, then you get something, yes, it rejects the fields inside. It definitely does that, but the problem is now we've set it to the same potential as the outside, so that's changed what's going on here in the charge distribution. So we're getting the charge on this thing as necessary to stop the electric field from existing inside, and that means it's disturbing the electric field distribution we had before by quite a lot more than a dielectric would. So it's offset this thing at the center, right? You see we've got this higher electric field because it's reasoned, well, in order for this to be a potential of 0 there and there and still have everything work out, we need to have enough, we need to have the right kind of charge there. So I guess a negative charge specifically, that we've got an electric field even at the center that's non-zero, so it's shifted things a bit. It gets worse if you get rid of this this specification of a boundary condition, value of V is equal to 0. on the exterior, now things have shifted even more. So we've got, to have this be the equipotential of 0, we need to have the right kind of charge showing up on it. On the surface of this, that moves the electric field even more than what we were expecting. So no, that's not quite what we do. We don't set the value of V is equal to 0 on this box to make it work out perfectly. But it's kind of on the right track. So if you look at this plot, then maybe we can not disturb what's going on in the interior by setting the V on this box equal to the value that we would, something like the value that we would have here, which is about, I guess, 2.8 E10. So let's give that a shot. Value V 2.8 E10. Aha. So now we've completely fixed it to an equipotential on that surface, made it a value that's close to what the potential was before. We have adjusted the electric field a bit, right? Like we've still got 0 at the center, but then by having this be an equipotential, we're drawing more electric field through the center of this rod because of that negative potential that we've got there, yeah? And this ends up giving us a bit of an interesting plot of electric field versus position compared to what we might have guessed. The polarization doesn't actually matter anymore because we've just gone and said that the electric potential is flat out uniform on the surface of this. So this carries the dielectric towards its extreme limit here. So conductors and electrostatics are kind of neat, but conductors in steady-state current are quite a lot more fun. So we're going to explore these in this different domain. In steady-state current, a material that behaves according to Ohm's law is going to have a current density that is proportional to the electric field. Electric field drives the current to flow in this imperfect conductor. So what's going on, you'll learn more about in third year. To talk about it a little bit, we've got an electric field that accelerates an electron a bit. The electrons are zipping around at hundreds or thousands of meters, hundreds of thousands of kilometers per second, really. They're zipping around and they're smashing into each other. They're smashing into other stuff inside the atomic lattice, inside a solid, and they lose a lot of that energy and just collide with each other. So they lose that velocity. They're constantly accelerating and then picking up speed and smashing and stopping. What an electric field does is it doesn't actually get a chance to accelerate the electrons very far before they smash into something and then and have to start over again with this velocity. But it does lead to a steady state small net velocity if you were to, on average, if you average over time. So rather than just sort of smashing around randomly and not really getting anywhere, they end up with a small velocity called the drift velocity of like millimeters per second, and that's how current is actually carried in most material. So in metals, that's the picture that we're going to be going with. That's called the Drude model, and you'll get to explore that a little bit more in a solid state physics class. Anyway, this is what we're talking about when we say that the conductivity, the conductivity is the proportionality constant between current density and electric field. This is just Ohm's law. So if you've ever used Ohm's law, you've been assuming this kind of a model for electrical conduction. It's quite parallel to heat flow. So if you compare this new thing, Ohm's law, to what we were talking about last week, you can see that the heat flux density being proportional to a conductivity and a temperature gradient is exactly the same as a current density proportional to an electrical conductivity now and a voltage gradient. So everything we said before, where temperature is like a driving potential for heat flow, and heat is going to flow from high temperature to low temperature according to the conductivity in a solid, is exactly the same here for electricity flow, current flow. Electrical current is going to flow from high potential to low potential according to the conductivity. Now with heat flow, that heat flux density was leading to changes in internal energy that then led to changes in temperature through heat capacity. For electrical current flow, something similar is going on, and we can just use rather than energy conservation, we'll use charge conservation to say that the divergence of the current density has to be the rate of change of the charge density. So think about this for a moment. If we have divergence of current density, that means that we've got net current leaving this point, which means the charge density there has to be decreasing, because where's that current coming from to diverge from that point if not from decreasing charge? So if charge is conserved, then you have that the divergence of J equals del rho by del T, where rho is the volumetric charge density. In steady state conduction, where you can't have things like the charge density changing in time anymore, then this means that the divergence of J is equal to 0. So we end up with an equation that's basically the same, but with a different meaning for the constant and a different physical meaning than of what we're solving for, as we had in dielectrics. In dielectrics, we were saying that the divergence of negative epsilon grad V is equal to the free charge density, which often is 0. Whereas now we're saying the divergence of negative, not epsilon, but sigma of grad times grad V is equal to 0. And now we're talking about steady state electrical conduction. Let's try and extract a little bit more meaning here. The resistance of an object is defined as the voltage across it divided by the resulting steady state current that flows through it. So this is how you maybe know Ohm's law. And how does this thing end up giving us this thing? Well, let's get there. So the current is the flux of the current density through some surface. And if we take a rectangular prism, because that's just an easy shape to talk about, the total current would be the integral of J across like one of the ends, or maybe any of the cross sections inside, and this should be sigma E if Ohm's law works. And then if E is negative grad V, then this thing integrated over the surface should perhaps be a constant because of the symmetry of the rectangular prism. If we just imagine one voltage on one side, another voltage on another side, if everything's smooth and linear, and the current has to be the same from one spot to the next across this prism, because we're not building up charge anywhere, then that gives us that the gradient of V is just delta V over L. And then with that being a constant, we can take it out, and this just becomes sigma times the area when we integrate over the cross section. So we've got sigma delta V over LA. So the other things in here are constants, right? The A, the sigma, and the L. For some material and for a rectangle, we've got constants for that. So that means the resistance, as long as we define resistance for this material as L over A sigma, then we've got that delta V is IR. The next fun thing for conduction is Joule's law. So in a situation where you've got work being done by the electric field, we can say that the work done is QE dotted with R. So this is QE is the force and R is the displacement that happened. So if we're talking about like charge that is moved across by a distance R, or a displacement vector R, then that would be the work that's been done by the electric field, if the electric field is what's making it move there. So here in this steady state conduction, it's happening because of this electric drift. So we use the drift velocity and say that this is the rate of work being done. So this is the W dot. So rate of work being done would be QE dot U, the drift velocity. Now per unit volume, we can convert this into a little bit of differential charge, right? So dQ is the density of conduction charges, so charges available for conduction times dvol, which would be cross-sectional area, and dr. So substituting this in, we get a little bit of rate of work done by the electric field is rho conduction, drift velocity, and electric field dotted with that. So this is per unit volume now. All right, so given this stuff, what we've got is rho conduction U drift velocity. That would be the current density vector. So this is density of charge available for conduction multiplied with the net velocity that the charge is having in conduction, and that would be, so net on average velocity here, that's the current density. So this is how we get E dot J is actually the rate of work being done by the electric field. So that's all going into heat, because the electrons, after they reach one end of this of this wire are not moving any faster than they were at the beginning. So all of the extra work that's been done by the electric field has just gone into heat within this wire. So that's how we can talk about volumetric heat generation being E dot J. So, example, steady-state current. We're going to find the steady-state current and midline voltage for two resistors in series and compare with the theoretical values for I is delta V over the sum of the resistances and the voltage divider rule that tells us the voltage across one of them being its resistance over the total resistance times the total voltage difference. And we're going to test how much FlexPDE agrees with the theoretical value for different lengths, conductivities, and widths and all that. Okay, so we're going to start with, let's just get a new file here. So maybe we'll call it vidwork part 2. Okay. And let's incorporate the new stuff that we've got in this problem. Okay. So in the steady state conduction. So now we're still going to be saying that V is the variable that we're solving for. Except now we're going to say that we've got E is equal to negative grad V, but J is equal to sigma times E. And we'll need to define what sigma is. Sigma, let's see, we've got different perhaps conductivities, lengths, and widths. Let's say we're going to just leave this as a parameter and define it differently in different regions. So first, let's just say sigma is equal to 1, and then we'll set up some length. Maybe length is equal to, length 1 is equal to 1.5. Width 1 is equal to 2. So that'll be the width that we're conducting through. And then maybe we'll get another material and we'll say length 2 is equal to 2.5, width 2 is equal to 1. Okay, so we'll draw this out. We'll say region 1 is going to go length. Let's make the length an X this time. That's different than it was in the example. And we're going to go length 1 to width 1, and then 0, width 1 to close. And we're going to stay here. That sigma is equal to sig 1 maybe. Sig 1 is equal to 1. Sig 2 is equal to 1.5. Yeah, let's try that out. Okay, so then we'll say region 2 and we'll draw out something very similar, except we'll say that the conductivity is sigma 2, and we'll actually start this where the other one ended, L1, and then we'll go L1 plus L2, L1 plus L2 and use width 2, and then back to L1 and width 2, and then to close. Okay, so this is always a good time after the geometry to just try and see if we can get a plot of what's going on. So we'll say div of J is equal to 0 as our differential equation for steady state conduction. Okay, so we've got this as the setup, width of 2, length of 1.5, and then a length of 2.5 and a width of 1. Let's actually take that first width down a fair bit, 1.1, just so that we start with something that's more reasonable and we expect to be able to calculate a little bit better. Okay, now so how do we make this thing conduct? Well, we are going to set that there's a potential difference between this left side and this right side. So let's set this side equal to 0 volts, and we'll set this side equal to V max maybe. Okay, so let's start off with V max is equal to 5. And how do we get to that left side? Well, that would be this last part here after we're at 0 and W1, and then we're going to go to close. So we'll say value of V is equal to V max line to close. Great, so now we've set Vmax over there. The voltage is just 5 everywhere now because we haven't set it to anything else anywhere. And over here, we're going to put the value of V to 0. So where's that? That is when we're in between this line and there. So here we're over at the right side on the bottom. Then we're going to jump up to the top. So we need to change the boundary condition right here. So we'll say value of V is equal to 0. Then line to there. And then after that, we'll put the load of V back to 0. That's the default boundary condition to make sure that it's insulating on the top. We can't escape there. Okay. So let's paint this so we can see what the voltage is at different spots. We have the voltage decreasing more or less linearly from left side to right side, starting at 5 and then going down to 0. Just as a quick check, if we make one of these materials have a much higher conductivity, we expect it to be kind of like a current superhighway compared to the other one, so we get no voltage change across it. Let's do that for this one. So we'll do that by saying sig1 times 20, way higher conductivity. Yeah, there we go. So it's not changing at all the potential, and then changes a lot as we go across this. Awesome. Okay, let's get some checks going with theory here. So R1 theoretical should be equal to L1 over the first width times the depth, which would be kind of like into the page, but that's the same for everything. So we'll just imagine unit depth and not multiply that, times sigma 1. And then same thing for R2. R2 is equal to L2 over W2 times sig 2. Yeah, then we can specify what the midpoint, okay, first of all, what the current should be. I theory should be equal to delta V, which is a total voltage difference, which is just V max minus 0 over R1 plus R2. And let's compare that first. So how do we compare that? We'll put in a summary section. Report, let's see, report I theory. None of the things that we made it depend on position, right? Yeah, we should be good there. Okay, so we can just report that thing. We don't have to specify a location. And we might want to compare this with the total current that's going through. So how can we find the total current? Well, we'll need to put somewhere that we can integrate across, right? So we maybe can name one of these lines, maybe right here. Maybe after we get to 0 and W1, we could put start entrance 0 W1 and then just check that, oh, we maybe made some mistake. Do this. Oh, line to close is not going to work there. Line to 0 0. Nope, that's still also not going to work. Oh, we didn't finish this thing. Right. So getting rid of that. Yeah, well, we actually had more than one error there, but nothing has changed now that we fixed it again. I'm just hitting Control R to run this really quick, by the way, and then Control E to go back so we can fix things quickly. Then what we're going to do is, now that we've got this named entrance region, we can report the boundary integral of the normal of J along that location. So let's see. Does this... Oh, wrong spot for the bracket. Normal of J on the entrance. Yeah. All right, so that seems like the normal has worked out pretty well. It doesn't always work out that well. We can be more specific rather than normal specifies definitely a vector to the right. We'll just add this in so we can compare. And we'll dot J with vector 1, 0. Yeah, okay, so this is the current going to the right. We've got a current going to the right of 1.646, and we expect 1.65. That's pretty good. We can measure this at a different spot. So let's put in a feature. Start L1 plus L2 and 0. Line to L1 plus L2 and W2. And this is the exit. We also could have split this off in the interior part of drawing region 2, but we should be able to draw it just as an external feature, so we can specify this this integral directly. Okay, and we've got the same current going out this side as we have going in this side. That's good. What about at some arbitrary spot along the way? We can just pick some different spot and draw a feature there. So what about at L1 plus L2 over 2? Or even actually L1 plus L2 over 3. We have this non-horizontal line. This is, let's call it some mid thing. Yeah. So by drawing mid, maybe this isn't so great of a thing to draw because it doesn't always go to the top necessarily. Let's have it go the other way. Let's start at over 3 and go to over 2 there. Yeah. Okay, that's good. So it ends closer to W2, and we should be okay for that. Yeah. So now if we say report this thing on mid, by manually doing this dot product, we should have the same current flux through this. But it doesn't seem like that one is working out. Did we dot J with that vector? Oh, that's not normal to this line. Right, of course. So we'd have to dot it with a normal vector to this thing that goes from there to there. So let's say, oh boy, this is kind of complicated. Maybe it's not even worth doing this, and sort of better to skip ahead here. But if we go negative W2 and we go the difference in these things to the right, which would be a sixth L1 plus L2 over 6, then divide by the magnitude of this thing. How many brackets do I need? Magnitude 1, 2, 3, 1, 2, 3. Okay. Then we get finally the same current going through this funky line when we properly use a unit normal to find the flux of the current going through that. So even though we're crossing multiple boundaries, we should have the same net current flux going through that. Okay, so that's the total current, but the other things that we're going to need are not just the total current that's going through this, we also want to check the voltage divider. So for a voltage divider, we're going to need to know what the value of voltage is at the midpoint. Let's see, how can we compare this? Well, we can try reporting V at 0 to 0. Does that work? Report V at 0, 0. I think we need report eval, or actually, let's try val of V at 0, 0. You know what it is? It's a different syntax. It's this one, report V, comma 0, 0. You know it can only be one of a couple of different things. This is why you really want to try out a bunch of stuff and try it quick, because then you'll get the syntax. So val of V at 0, 0 is 5. We actually want at L1 and 0. This is the midpoint voltage. Now we can compare this with the theoretical one. So we can compare that with what we'd get from voltage divider. And voltage divider says it should be R1 over R1 plus R2 times V max. And let's see, 2.25 is what we get from voltage divider at the junction. Oh, you know what? This is not correct. This is what the voltage drop across the first one would be. So actually, we can use V max minus that. Yeah, 2.75. Or we could have used report R2 over R1 plus R2 times Vmax. The reason for this is that this is the voltage here relative to 0. So this is really the voltage drop across this one, and that is what's going to give us the absolute value of the voltage at this point. Whereas the other one is the voltage drop across this one. So to get the absolute voltage there, we need to have Vmax minus that difference. And that's what gives us our 2.75. Okay, so we've tested out the voltage at the junction. We've tested out the current going through the thing with theory, and things seem like they're agreeing pretty well. So the next thing is to try messing around with the values and see where this maybe breaks. It's not exactly the same. What if we change the widths to the same? Okay, so that seems almost identical. Maybe we'll get some reports at the end here. So we'll perhaps say report to the current error. How would we do that? We'll get any one of these. Maybe this one, the entrance one, that minus the theory one. What do we want to say is exact? We're going to say that, let's say that the theory is exact, supposedly. So this is going to be the error from theory as current error from theory. Now let's say, not that the theory is necessarily correct all the time, but this is, let's just call this relative current error from theory. Okay, so relative current error from theory is, wow, that's a really small difference. So it seems perfect at this point. We can also do something similar for the voltage at the midpoint, and there we'll say val of V at L10 minus this thing. Actually, why don't we give this a name too? So we'll call that V theory. V junction theory, I suppose. And we'll subtract off V junction theory and then divide by that. And that'll be relative voltage error from theory. Okay, cool. And as expected, if the current is agreeing this much, probably the voltage is agreeing a huge amount. So that's fantastic. Let's see, we've got, what if we put in different conductivity? So we say this one's 20. We have a very different value over there. Still almost no different from theory. Pretty good. If we make the lengths a lot, one length is way higher, so our grid density is jumping down. Still almost no difference from theory. Both are working out quite well. What else can we do? We can change the widths. So we'll change one of the widths to half as much. Aha, now we've got a 5% error in both the current and the voltage from what was going on in theory. Let's change this length back down to 1. And now the error jumps up even more. We've got a voltage error of 17% and a current error of 12. And let's make the conductivities very similar as well. It's not quite as bad as it was before, but we do have this pretty large error when the widths are not equal. So why would it be that we get almost no error no matter what we do to the length ratio or what we do to the conductivity, but we suddenly have this massive error from our theoretical calculations when we build in a different width? Well, one explanation is that with the width, we have more of a two-dimensional problem, so you do expect more numerical error than otherwise. But another thing is the theory is actually not correct for the width problem. We can see what this is like more clearly if we make this a really high conductor here. So now with this first one limiting the conduction, it's the limiting resistor because it's got a lower conductivity by quite a lot, even though it's a little wider and slightly longer. That's bad. Double the width is good, but it's got such a lower conductivity by like a factor of 20, I think. Yeah, that it ends up being the limiting resistor. So if we were to report R1 and R2, we see that R1 is quite a lot higher. Let's just estimate this first. So when we've got the width of it being double, so the conductivity being 1/20th, means that it should be 20 times higher resistance. Let's also report a ratio. Yeah. The length being 50% higher means it should be 50% more resistance. So 20 and then times 50% more is going to be 30 times more resistance. And then the width is half as much. So we expect 15 times more resistance. Let's check. Yeah, so 15 times more resistance for R1. It's got 15 times more resistance, so this is really limiting things. We actually get, I would expect, less current than theory. Let's check if that's the case. So I theory is 3.1, and we actually get a little bit less. So the reason for that is the theoretical calculation is saying that we can conduct all the way across the top, use all of the width all the way, and then when we get to here, no problem, we can just continue conducting in here. But actually, we can't do that. We have got to flow down through this and then across. They're not, this one doesn't connect to the other one perfectly. So the situation is going to be different if the bigger conduction one is wider than this one. So if we make this one, or if we just switch what the conductivities are, if we make this one 20 times as high as this, then it really doesn't matter that we can't actually jump up instantly into the higher conductivity one because we don't need to. It's going to be not a limiting factor on the resistance anyway. So just switching this to 1 and 20 should reduce the relative error quite a lot. Yeah, so we're now down in less than 1% relative error because we don't need to conduct across this, this lateral direction nearly as much as we did before. So it's okay, we can conduct there, we go across, yes, it's largely in the top and then just jumping down, no problem. Okay, we can get a little bit more information about what's going on by plotting the current density as well. So let's see, vector J. So yeah, this shows exactly what's going on with the current and demonstrates that it's not just left to right as we were assuming in our theoretical model, and that's where the limit is happening. So in this situation, the error from theory is actually not a numeric thing, but largely a conceptual thing in a which identified a limit in the theory.